Hello, I'm Bartomeu Pou, and I will present advances in multi-agent reinforcement learning for adaptive optics control. I'm from Barcelona Supercomputing Center and Universitat Politècnica de Catalunya, and this work is a joint work together with Florian Ferreira from LESIA, Eduardo Quinones from BSc, Damien Gratador from LESIA and ANU, and Mario Martin from UPC. Let's start by a brief introduction. In adaptive optics, the current state of the art is considered controllers such as the linear quadratic Gaussian or similar. These kind of controllers build a model of the atmosphere dynamics, but in the process they require some assumptions. For example, the assumption of Kolmogorov turbulence. Instead, we would like to create a controller without any a priori assumptions and based only on online data. And we will do this with reinforcement learning, which is basically learning by a trial and error controller. In this slide, we describe closed-loop AO. We will focus on systems that have a single Schack-Harman wavefront sensor and two deformable mirrors. On the right, you can see the typical closed-loop schema with a deformable mirror that corrects the incoming wavefront, a wavefront sensor that senses the residual errors, and the real-time controller that sends the commands to the deformable mirror to correct for those residual errors and the new errors that will come from the atmosphere. This kind of problem is usually solved with an integrator. For each frame, the wavefront sensor is able to obtain a set of measurements. Then those measurements are converted into commands via a linear relationship. And finally, an integrator law is used in order to avoid errors from sources such as delay. Now we'll explain how we can improve over that. First, a brief explanation of reinforcement learning. Reinforcement learning is a framework for agent-environment interaction. The goal is to learn a nonlinear function that maps states, which is information of the environment, to actions, which are the commands, and those actions should maximize a cumulative reward function that is a performance measure. This learning is done via trial and error, and we must define state, action, and reward for adaptive optics. On the right, you can see the same closed loop as before, but now we have reinforcement learning elements. We have the environment, that is everything outside of the real-time controller, and the agent, that is the real-time controller. The agent receives the state and processes an action, and this will maximize the reward. Before defining those three elements, state, action, and reward, we need to take a look into the different challenges of applying reinforcement learning to adaptive optics. Due to the limited time, we will only take a look on three of those problems in this presentation, which are the number of samples required for training, changing atmospheric conditions, and high-dimensional state action spaces. So first, the number of samples required for training. As we are training online from data, we would like to perform well in the minimum amount of time possible. So we want to minimize this number of samples required for training. For that, instead of training a full controller from scratch, we use the integrator and we send actions to correct the integrator commands so that the number of samples required for training is minimal. This is called residual policy learning in reinforcement learning, and we will use that. The second challenge is changing atmospheric conditions. We would like our controller to adapt to dynamic atmospheric conditions. However, as reinforcement learning continually learns, so we will do experiments to check if the continual learning is enough to adapt to those changes. Finally, we have high-dimensional state action spaces. The initial experiments use command-zonal basis. That means that for each element of the command vector, it modified directly one actuator. And this only showed promising results for low dimensionality problems, system configurations with a low number of subapertures, and actuators in the deformable mirror. In machine learning, we have this problem that is called curse of dimensionality, that the problem complexity increases exponentially when the number of dimensions of the problem increases. Instead, we switch it to a global basis inspired in the Zernike polynomials, the so-called BTT basis. And this BTT basis is orthogonal between all the elements, so we use the orthogonal property to separate the problem into easier subproblems. Now we will have one agent per set of modes, I will have multi-agent reinforcement learning instead of single-agent reinforcement learning. So with this multi-agent reinforcement learning, we have n agents where each agent controls a set of modes and will sense that set of modes in the state. So basically the state has the residual commands from the integrator and the time step only for the modes that it will act, and also a history of those modes in order to better characterize the atmosphere evolution. Also, the actions will be one per agent, but they will be joined into a joint action in order to finally modify the integrator law, as we told before that we are using a residual policy learning. Finally, we also need to separate the reward function into different agents, and we did that by the goal of the reward function per agent will be to minimize the integrator response on the modes it's controlling, and that is why here we are using a minus the sum of the response of the modes it is looking. In these definitions, we have that the M uppercase that indicates the set of modes that the agent is controlling. On the right also, we can have a look at the final diagram for this problem where we have the environment and we have the real-time controller. The real-time controller has the multi-agent part where the state is separated into n states and the actions are separated in n actions. Finally, they are joined into the joint action, and this is summed to the integrator law to have the final command. As an additional information, we found out empirically that sharing neighbor non-control modes on the state improve performance. So basically what this means is that for agent I, if it looks at the states of I plus 1 and I minus 1, it will achieve better performance. Only on the state, the actions will be the same, just the actions it has to control. And we hypothesize that this because the modes are quasi-orthogonal and they are not pure orthogonal, and some statistical information from neighbor modes can be used to obtain better performance. So now let's get into the results. First, let's explain the experiment parameters that we have used. There are a lot of parameters, and due to the limited time, we will only explain 3, but you can take a look on the right to the different parameters we have used. We have used Compass as the simulator for our experiments, and then we have 3 important parameters. That is, we have used a telescope with 8 meters of diameter and with a shock Harman of 40 by 40 subapertures. We have also simulated the atmosphere with 3 atmospheric layers, and we have done 3 experiments with different wind speed profiles, where the average has different value. You will see more later. We have done more experiments than this, but as we have limited time, we will only show a few. So this is the first experiment. Here we tested the 3 different wind speed profiles on the 3 different controllers. We have the controller of multi-agent reinforcement learning, integrator, and the multi-agent reinforcement learning with shared states within neighbor modes. On the left, we have the 3 different values of wind speed profiles. If you go above, you have more average wind speed over the all layers. And what you can see in the different experiments is that we have on the y-axis the long exposure state ratio, and on the x-axis we have the frame number of the experiment. Initially, as you can see, the reinforcement learning performs catastrophically, but after some time it can outperform the integrator with a wide gap on the hardest problem, also a wide gap on the normal problem, but on the easy problem with a very low wind speed, we achieve similar performance, but with a slight gain here. Also, what's interesting to see is that more or less in all the 3 experiments, the multi-agent reinforcement learning achieves approximately the same performance, meaning that it's probably tackling temporal error to its full extent. Finally, the window model, we can see that outperforms the original model, as the problem difficulty increases. So perhaps it's a good idea to share these features between states. Then we have more results. We compared with LQG. We run, after training, we fixed the weights of the neural network, and we trained for, we test for 20,000 frames with 3 different sets. Remember that LQG needs a priori assumptions, and in this case, LQG knew exactly the parameters of the atmosphere that it used to do the prediction into the future. Again, here we have the 3 different wind speed profiles, and here this time it's increasing from right to left, and we have 3 controllers: the integrator, LQG, and multi-agent reinforcement learning. The results are showed in mean and standard variation, and in black the winners for that wind speed profile. You can see that both LQG and MARL outperform the integrator with a wide gap, and if we compare LQG and MARL, MARL achieves better results on the harder problems, and LQG outperforms MARL by a very small margin in the easiest problem. So we can say that we achieve better or almost equal results in all the experiments than LQG. And we don't need any a priori assumptions of the atmosphere. So if LQG does some assumption of the atmosphere that is incorrect, we will get even better performance. Finally, we want to show an experiment with changing atmospheric conditions. Basically the same, you have frame number and long exposure stir ratio with the 3 controllers, and we train with a fixed atmospheric condition, and we change at 1 million frame. Here you can see that we change from wind speed profile 3 to wind speed profile 2, and wind speed profile 2 to wind speed profile 3. So here the wind speed becomes harder, and we can see that after the change, both MARL and window MARL still outperforms integrator, and even outperforms in a greater extent. On the contrary, as the problem becomes easier, on the right, we can see that MARL and the windowed MARL decrease the gap between the integrator, but still outperform it. And you can see that the gap widens as more training time is allowed in the end of the graph. Finally, let's get into the discussion. We have presented a MARC controller for AO control. We have seen the MARC controller outperforms the integrator and has similar performance to LQG without requiring any a priori assumption in an 8-meter telescope with a 40 by 40 Shank-Harman wavefront sensor, and it appears to be robust to changing atmospheric conditions. As future work, we want to test the more realistic changing conditions or in a real-life setting, because we have changed after 1 million frames. And what's better is we are trying to use another sensor. It's the pyramid wavefront sensor, because the nonlinearity of the pyramid wavefront sensor will allow us probably to get even better results than the integrator. So this presentation is based on the results on an under review paper. So if you liked it, check the paper when it's released. Thank you so much, and if you have any questions, you can send me an email or ask me via Discord.